Dear all, welcome back. During our previous discussion, we considered aircraft as a rigid body which has 6 degrees of freedom in space, and we classified the motion of the aircraft into two phases. The first one is the longitudinal case and the second is lateral directional case. And the longitudinal case is a single vertical plane motion where it can translate along the body x and body z axis and all associated with a rotation about y axis called pitching moment, right? And we also looked at what is lateral directional motion, which involves two rotations and one translation along y axis, and the rotations here are rolling motion as well as yawing motion, which is about x axis and z axis respectively, right? So we have an aircraft So let's define an axis with respect to which all the components of this aircraft are mounted. Let's say this has fuselage reference line, right? So we'll use this fuselage reference line while talking about stability of an aircraft here. So now let's consider a body axis system. So we have wing, let's quickly go through this major components of this aircraft. Say we have wing, right, and a horizontal tail, and a vertical tail, right. So these are the three major components which are indeed fixed components of aircraft along with the propulsion system, right. So, and we also have some small moving surfaces that are attached to this aircraft, fixed components, right. So these moving surfaces, when deflected at certain angle with respect to the flow, right, say this aircraft is moving at certain velocity v infinity, making an angle of attack alpha with respect to this free stream velocity, right. So when we deflect this control surface with respect to this flow at certain angle, so this will alter the local aerodynamic forces which generates moment, right, about CG. Let's say this is my CG, this is my CG. So the change in aerodynamic force after the CG or at an offset location with respect to CG will produce a moment because of it, right. So this moment is because of this moment the aircraft orientation changes, right, orientation in space changes. So the surfaces with which we control the aircraft orientation is known as control surface, right. So the control surface on the horizontal plane is elevator, horizontal tail, which is on the vertical tail is rudder, and on wings we have ailerons, and we also have some high lifting devices called flaps attached to the wings. So flaps are majorly to enhance the lifting characteristics while takeoff and landing, whereas ailerons, rudder and elevator are to control the orientation of the aircraft throughout the flight. So we call them as control surfaces. So these are the moving components here, right? And then, of course we have propulsion system, either a propeller driven or a jet driven aircraft or a UAV, right? And we said that we have 6 degrees of freedom of motion here. So let us consider the origin of this coordinate system at the CG itself, so which we discussed during the previous course, and let the x-axis be pointed towards the nose of this aircraft from the CG location. So this is our x-axis of this body coordinate system. And then we have z-axis, which is towards the undercarriage, right? So let O be the origin of this coordinate system, which is coinciding with the CG of the aircraft. And then so let Z be towards the undercarriage, and then we have, so we are considering a right-handed coordinate system. So Z is in the downward. So X cross Y is Z. So what we have is the second axis, which is Y axis here, right? Which is into this board here, right? So we have defined aircraft motion in two modes. So the first one corresponds to longitudinal motion. You can also say this as a single plane motion, right? So for an aircraft or a UAV, we assume there exists a plane of symmetry. What exactly it is? We have a vertical plane about which the geometry, though it doesn't look symmetric here, but in reality we have the geometric we call symmetry about that vertical plane as well as mass distribution. The symmetry in mass distribution. Okay. So if the aircraft is moving in that particular vertical plane, or the motion is constrained to that particular vertical plane or the plane of symmetry, we call such a motion corresponds to longitudinal motion, right? So the aircraft can translate along x-axis and z-axis, which corresponds to this vertical plane of symmetry, right? So there are two translational motions, and it can also have a rotational motion in this vertical plane. So the aircraft is not crossing this vertical plane, so the motion is still constrained to this vertical plane even during that rotation, right? So we have translation along x. So in longitudinal plane we have 3 degrees of freedom, to translation, so which is along x-axis and z-axis, right? And one rotation. So rotation is due to moment, as we discussed. So we have pitching moment, which is the rotation about y-axis, right? So what we have is pitching moment, which is given by q, right? So the pitching moment is, so for a longitudinal motion, what we have is, so let u be the translational velocity along x and w be the translational velocity along z axis, and say v be the translational velocity along y axis. Now what we have is, so you have u, w, and uw and q, right? So the corresponding, what is q is the corresponding pitch rate, right? The rate at which the aircraft is changing its pitch orientation. So because of this pitching moment, say m, let this pitching moment be m in the longitudinal plane, denoted by capital M, which is given by half rho v square s cm, where cm is non-dimensional pitching moment coefficient multiplied by the characteristic length along this longitudinal axis, which is the mean aerodynamic chord of this wing, right? So you can, right? So this pitching moment creates a change in orientation, and the corresponding change is, or the orientation change in theta, right? So we have because we have a rotation about y-axis, which changes the orientation of this aircraft, given by theta, and the rate at which this theta is changing is q, right? When there is no other rotation involved. So q is the pitch rate, we call it as pitch rate. Theta is the corresponding pitch orientation. Okay. So U and W are the translational velocities here. So how can we generate this pitching motion? How this moment is generated? We know if we can generate a force at an offset distance from the CG in the longitudinal plane, that can create a moment here, right? So about y-axis, if I have to produce a moment, then I have to produce a force in this vertical plane at an offset to the CG, right? So we have a control surface for this longitudinal control called elevator, right? When you deflect an elevator, it changes the aerodynamic force there, which produce a moment about the CG, right? So the corresponding deflection at this control surface, let us say if I take the cross section of this tail, so this particular attachment is a moving surface for this horizontal tail, right, which is a shorter version, a smaller version of this wing, right? And in general, this is a symmetric wing. We'll discuss why it is. So when we deflect this particular control surface, say if we deflect this control surface down, right? So this deflection obstructs the flow here. You can say changes the camber of the aerofoil, or you can say you obstruct the flow, right? So the flow gives a reaction in the upward direction. So this produces a force, net force upward direction. So about CG, this force produces a moment, right? Pitch down moment here, pitching down, right? So let us also define the convention here. So about y-axis, so if you stretch your thumb along the positive y-axis, the curl of your fingers will give you the corresponding positive rotation, right? So pitch up is positive, so nose up. What is the positive rotation about y? If the aircraft rotates its nose up, right? So whatever the moment that helps the aircraft to rotate its nose up is called positive moment, right? Corresponding moment is the positive moment. And if the aircraft is rotates its nose down due to that moment, we call it as pitch down moment, right? And it is considered negative, right? So and Q is considered positive when it is pitching up, when the rate is changing in the with the nose up direction, and theta is also considered positive when the aircraft nose is up, right? So pitch up is positive. So for moment is positive when it is pitch up, right, which is nose up, and this moment is negative if it is pitch down or nose down. Okay. So similarly, we have lateral directional motion. So any motion that cuts this vertical plane of symmetry is known corresponds to a lateral direction, corresponds to this lateral directional motion. So what are all the possible cases? Translation along y-axis. So this aircraft has to cut this plane of symmetry. Say let this black board be the vertical. So this board be the vertical plane of symmetry. So aircraft moving in and out of this aircraft, of this blackboard is translation along y-axis, and this corresponds to lateral directional motion. So it has again 3 degrees of freedom, where the first degree of freedom is due to translation along y-axis, and you have 2 degrees of freedom by means of rotation here. So one rotation can be the wings rolling, right, rolling up and down. And the rotation about x-axis is known as rolling motion, right? So and the positive rolling and the positive roll is given by. So what we have is roll about x-axis, and we have pitch about y-axis, and you have about z-axis. Okay. So the positive roll is given by stretch your thumb along the positive x-axis, and the curl of your finger will give you the direction of positive roll. So corresponding rate is the roll rate here given by P, right? So what you have is roll and yaw, right? So these two are rolling motion and yawing motion are due to rotations, right? So which are caused by moments. So the corresponding moment about x-axis is known as rolling moment. So rolling moment is given by rolling moment. So is represented by small l, right, which is half rho v square SB times CL, where CL is the coefficient of rolling moment and B is the span of the wings, right? So CL is coefficient of rolling moment and B is span of wings. And we also have a moment about z-axis which makes the aircraft to rotate about this particular axis. That will help to orient the nose in the horizontal plane, right? So that change the orientation of this aircraft in the horizontal plane. So that is known as yawing motion. So it is again, or it is due to, so that particular motion is known as yawing motion. So this is rolling motion, which is rotation about x-axis and rotation about z-axis. So rolling motion, z-axis is yawing motion and is given by, the corresponding yaw rate is given by r, right? And so due to this, it results in a change in orientation in the horizontal plane, right? So the aircraft nose initially say along this particular direction. Now due to a rotation about yaw axis or say z axis, the aircraft nose is now oriented in a different direction. So this particular change in orientation is given by xi, right? So under no other rotation, so this xi dot is equals to r, okay? That is single plane rotation. So xi dot is equals to r, and the positive yaw is given by right wing going back, right? So if you stretch your thumb along the positive z axis, the curl of your fingers will give you the corresponding positive rotation, where the right wing going back corresponds to a positive yawing moment, right? So and right wing going down is positive rolling moment, okay? So stretch your thumb along positive x, the corresponding curl of your fingers will give you the rotation, positive rotation of roll. So yawing moment, so which is given by capital N, which is half rho v square dynamic pressure times the area will give you the force, and the corresponding non-dimensional force coefficient times B, reference length here, right, where Cn is the coefficient of yawing movement. Right. Now what will be the positive control surface deflections? So the direction in which, so let us say we deflect a control surface, and if that deflection produces a corresponding negative moment, right, then we consider that particular deflection as positive. For example, in case of elevator, stretch your thumb along positive y-axis again, right, y-axis, and the curl of your fingers will give you the corresponding positive rotation here. So elevator moving down, so this was the reference, and now we have deflected it downwards, right? So say say this is the current deflection of this elevator. Okay. This particular angle is known as delta E. When you deflect it down, there is some upward force, right? Because of the change in camber here, there will be increased lift at the same, like for the same angle of attack that we are seeing, right? Or you can say we are obstructing the flow, right? So that flow will give you a reaction as an upward force. And this change in force at the tail will produce a moment here, right? So this moment will be rotating the aircraft nose down. So nose down is negative moment. So pitching moment. So the moment that you have is negative pitching moment, isn't it? So when you have, if the deflection contributes towards negative pitch, corresponding negative moment, right? So then we consider that as positive deflection. Delta E is positive when it is deflected downwards, and negative when it is deflected upwards. So you can say, so if this is delta E, then it is negative, right? So elevator is what creates the orientation control along the pitch axis, isn't it? In the longitudinal plane. So controlled by elevator shear, right? So the corresponding moment that is generated due to elevator deflection is a pitching moment, isn't it? So if this elevator produces a negative pitching moment, deflection of this elevator helps the aircraft with a negative moment, then we say that particular deflection is positive deflection. Now similarly, we have ailerons here. So when we deflect an aileron, right? So the deflection, so the rotation, the corresponding rotation will be about x-axis. Why? Because with respect to CG, we have two ailerons on both the wings, right? At an offset location along y-axis. So when there is a force, upward force, at an offset, y-offset, that creates a rolling moment, right? Let us say this is my aircraft, that is the nose of the aircraft, and this is, or say this is the nose and that is the tail. Say I have one wing here. Let us say I have a wing here, right? So this is my nose, and these are my wings. Okay. So I have one control surface here, and there is another control surface here. So we have two ailerons located on the wing, right? So one on the right and the one on the left wings, or one on the port side, the other one is on the starboard side, right? So when we deflect this particular aileron, and again we see it is located towards the tip of the wing, right? So and this aileron, when deflected, will produce a force, right? So when I deflect, let us say, stretch your thumb along the positive x-axis. Now say the x-axis is towards the nose here. So the corresponding curl of your fingers will give you the corresponding positive rotation of the control surface as well. Not only the rotation of the aircraft about that axis, but also the control surface rotation. So now, so my fingers are pointing towards downward motion of this particular control surface. When I deflect this downward, what happens is it produces a force upward, isn't it? So these two ailerons are deflected in opposite direction. When I deflected that right aileron down, so the left aileron will be deflected upward, right? So this is how in general the convention is. And the average of these two deflections is the actual control surface deflection of the ailerons, right? So when you deflect this up and this down, right? So when you deflect it down, we have an upward force. When you deflect it up, you have a downward force. So this upward force will contribute towards a negative moment. Even the downward force from here multiplied by this offset distance contributes towards a negative moment, right? So the positive deflection is deflecting right aileron downwards, right? So if you deflect this downwards, deflect this aileron down, let us say this is the new location of the deflection. If you deflect this downwards, right? If you deflect it down, then we say this is positive. So here, if I take a cross section, if I take a cross section there, so say this is my wing section, and this is a corresponding control surface attached to this wing section, right? So if I deflect this downward, the right aileron. Right. So if I deflect this aileron downward, so I consider this deflection as positive delta A. On the other hand, when I deflect it up, right? So if I deflect, so let us say, so this is my nose. So if I deflect this up, the aileron will change the local aerodynamic force there, right? So the resultant local aerodynamic force will be acting downward, right? And then when I deflect that up, I have to deflect this down. That is how the convention for this ailerons is. If I deflect this down, so this will produce an upward force. So that will produce a positive rolling moment. So the downward force and the upward force, right? So multiplied by the corresponding moment arm here will produce a positive rolling moment. So positive rolling moment is right wing going down. So I say this is my right wing and this is my left wing. So positive deflection is right wing going down. Right? And if I have to consider rudder here, so if you look at from the top view, so if you look at from this top view, right? So the rudder cross section will be, again it's a symmetric tail, symmetric vertical tail. So this is how the rudder looks like, and then it is attached with a small moving surface called rudder, right? That is what we discussed just now. And when you deflect this rudder, it has to produce the corresponding yawing moment, right? So the usage of rudder is to change the orientation in the horizontal plane. We generally call it as heading, right? We try to change the heading of this aircraft by deflecting this rudder. So which direction, what should be the deflection of this rudder so that it will produce a negative moment towards the left or towards the right? Yeah. So when you deflect this rudder towards the left, what happens? I deflect this rudder towards towards me. Let us say, if this is the control surface, if I deflect this rudder towards me, so this produces a force into the board, right? So that force acting at an offset distance with respect to CG. So it has a longitudinal offset here as well as vertical offset, but let's talk about the longitudinal offset here. So this longitudinal offset and multiplied with that force that is produced by the rudder creates a yawing moment, right? So that yawing moment is negative, right? So it is rotating left wing out, right? Left wing back. So the yawing moment that rotates the left wing back is negative yawing moment. That's what we just discussed. So that means when the rudder deflection is producing a negative yawing moment, the corresponding deflection of that rudder is known as positive, right? Is considered to be positive. So if I have this rudder deflected towards left side, right, here, that means what is, so if you place it like this, you just translate it and place it like this. So if you deflect this outside, right, so then it is considered as positive delta R. So positive delta R results in negative N, negative yawing moment, right? So what we can conclude from here, positive delta E produces negative pitching moment, right? And positive, okay, so positive rudder deflection will produce negative yawing moment, and positive aileron deflection produces negative rolling moment, right? Isn't it? So what is positive elevator deflection? Deflecting it down. So the positive corresponding positive deflection is deflecting it down, right? So here it is towards left. So when you are facing the aircraft from the tail, right? When you are facing the aircraft from the tail, so then the corresponding deflection towards rudder deflection towards left side is considered positive. Right? Similarly, So aileron deflection, right down. So right aileron down. So if I deflect this right aileron down, that is considered as positive aileron deflection. And in general, this is taken as average. No, the aileron deflection in general is average of this value plus, left side and right side aileron deflection value. So if you want to talk about the flying characteristics of this aircraft, first we need to talk about an important property called stability of this aircraft, right? So stability is a property of equilibrium state, right? And we have defined earlier what is equilibrium, and we all know it is a state about which resultant forces and moments are zero, right? So if you want this aircraft to fly, right, first of all we need to talk about whether the aircraft can fly or not. So stability is the concept that talks about whether about the flying qualities of this aircraft, right? So stability is a property of equilibrium, right? And equilibrium is a state about which resultant forces and moments are zero, right? So what we are going to talk about is stability as I mentioned, it's a property of equilibrium, right? So what is equilibrium? When we say body is in equilibrium, so when the resultant forces and moments acting on the body at that particular state are zero, right? So we say equilibrium corresponds to, it is a state of system about which resultant forces and moments are zero, or no net forces and moments acting on the system, right? So let us consider the following three cases just to talk about the equilibrium state. What are the various equilibrium states, right? So we should first consider an example. So let's talk about that with the help of this example. So let's consider a concave up, right, surface, and let's place a ball on this particular surface. Let this point be O, right? See, this one is concave up, right? At the same time, consider another surface on which the ball is again resting, right? Let this position or the location be O prime, right? O prime. So this is convex up. So let's assume this as a flat surface, right? And the same ball is placed on this flat surface here. Let this location or position be O double prime. So this is on flat surface. So let's understand what are various types of equilibrium with the help of this example. So in all these cases, if you observe, the ball is at rest. That means the resultant forces and moments acting are zero, which implies the ball is at equilibrium in all the three cases, irrespective of the surface on which it is resting. In all the three cases, the ball is at equilibrium, right? In the first case, so when we displace this ball from this equilibrium, let us see what happens in these different cases. Now, how can we displace this? With a gentle push, isn't it? So let's give such a gentle push for this case A, where the ball, so due to this push, the ball will try to roll up the surface, isn't it? It will try to go up the surface here, and then it may reach a location, say A. So this corresponds to the point where the velocity of this ball becomes 0, right? And once it becomes 0, then what happens is, we know it will come down, right? It will come down towards O, and then it will overshoot O and may reach point B. So the same ball may reach point B. So again, B corresponds to 0 velocity. After that, again it may start moving back towards O, and this oscillation continues, right? So at some point, let us say, once the disturbance is dissipated, right? So this, or damped, this particular ball will try to reach at or attain this point O, which is the initial equilibrium state, right? So that particular equilibrium is known as, or is defined as a stable equilibrium, right? So consider the second case. So the ball is at equilibrium, which is O prime here, right? So when you displace this ball, what happens is it will try to roll down the surface. It will try to move the surface completely. So it may not come back to its O prime, right? So it's same case, like even if you displace to the other side, so the ball may not come back to this O prime. Right. So the system here, the ball is not able to attain the initial equilibrium, which is O prime, right? So in this particular equilibrium is defined as unstable equilibrium for this system, right? So in the third case, we have a ball here. So when you displace this, what happens? It will translate to a new location and try to attain a new equilibrium. Let us say O triple prime, right? So in this case, it is not coming back to the new equilibrium, but it is trying to attain another. So sorry, it is not coming back to the previous equilibrium O double prime. Instead, it is trying to attain new equilibrium O triple prime. So such a case is defined as neutrally stable equilibrium. Okay. So with this, let us define what is stability. So it is the ability of the system to re-attain the initial equilibrium So once you disturb the system from that initial equilibrium, it should have the ability to retain that equilibrium state, right? Such a system we call, if the system have that property, then we say it is a stable system, right? So for us to understand about this stability, we need to talk about, so in order to define the stability of the system, we need to talk about two cases called static stability and dynamic stability. So in this case, in the first case, see, the system is stable here, right? That's why the equilibrium, we said stable equilibrium. So the ball tries to oscillate about this O and finally reaches O here, right? The same, so in the other case, we call it as unstable equilibrium. And the third one is neutrally stable equilibrium, right? So where in the second case, it's not able to get back to that initial equilibrium state. So it is not stable. The system is not stable here, right? Here the system is neutrally stable. Now, what is static stability? So whenever, in this particular example, whenever this ball reaches to a maximum or say zero velocity location, or the maximum location or the zero velocity location here, it will try to return back towards the initial equilibrium point. So whether it stops there or not, we are not worried, but at each and, if you look at these extreme points, at each and every time it has a tendency to move back towards this equilibrium location, initial equilibrium, right? So that initial tendency to come back towards this equilibrium is known as static stability. It is a initial tendency to return to equilibrium. Right? So, what is dynamic stability? So, generally dynamic stability talks about the time history of motion of the system once disturbed from the equilibrium. Right? It talks about how long it takes for the body to reach the equilibrium, or whether it reaches equilibrium or not. So, in order to understand this better, consider this example. Right? Consider this slope, right? So a slope surface with slope, right? And there is an abrupt obstruction towards the end of this slope. Right? Now let us say initially we place this ball here on the surface at this junction. Okay. Now it is in equilibrium, definitely we know that. And once we displace this to a new location, say, let us say this is O and this is say O prime, right? Once you displace it, so the ball will try to automatically come back towards this equilibrium, isn't it? So if I plot displacement with time, say this is my equilibrium, what I can notice is, so this is my equilibrium. I'm initially this is at equilibrium. I'm trying to take this to another location. I'm trying to displace it and then leave that object, right? So what it does is it will try to achieve this equilibrium with time, right? So such a system or such a process through which it achieves the equilibrium is known as subsidence. So let's consider the other case. Again, here we are talking about time history of motion once we disturb, right? So that pertains to dynamic stability. Okay, isn't it? We are talking about, so this is the initial amplitude. So at each and every time, this initial amplitude of displacement is decreasing with time, right? So this particular value is keep decreasing with time. And consider the other case. Let us say we place this object here. Let us say somehow we made this ball stand at this particular location, right? Let's say the initial part may be a bit flat compared to this curve. Okay. So this particular equilibrium may be O, right? So once you displace this to a new location here, to O prime, what happens is this ball will try to roll off this surface. So again, if you plot this particular, so say let's assume the magnitude of displacement is same, where we have displaced to this particular location. So what happens is with time the displacement increases, right? So what do you mean by displacement here? So it's an offset from the initial equilibrium location, right? So with time it is moving towards the equilibrium. That means the displacement is keep decreasing. In this case, the displacement is keep increasing. Is keep on increasing, right? Why? Because it rolls off the surface, then the distance between O and O prime is increasing, right? So this particular, so here you can see, so this particular initial displacement is nowhere reducing. In fact, as the time progress it is increasing, right? So this particular case is known as divergence. So with time it is not able to reach the equilibrium position, so we call it a divergence. So it is dynamically unstable. So if with time, if the object reaches the equilibrium, then we say it is dynamically stable, right? So for a stable system, it is essential, it should satisfy both dynamic stability as well as static stability as well as dynamic stability, right? Now let us consider a different case. So these are not non-oscillating motions, right? But aircraft is so we can consider it as a second order system. So in general have an oscillatory motion, right? Once we disturb the aircraft from its equilibrium position, so it tries to oscillate about that equilibrium. It has certain oscillatory motion. So it's a second order system, okay? So I'm trying to get back to that by raising this example. So one easy way to visualize this is consider a second order system with a spring mass damper or a simple pendulum here. Right. Okay. So let us say L be the length of this pendulum, which is pivoted about point O prime, and the weight of this bob, which is hanging at the bottom of this length L, at the bottom of this length L is say mg, right? Which will be acting perpendicularly down, say. So this is perpendicular to this ceiling, okay? And now let us displace this object to a distance. So in this case, the tension acting in this string is balanced by mg, and we can say this is an equilibrium state, right? And it is at rest, it is not moving. Now let us displace this bob by an angle theta. Right? So say this is the displacement theta, right? L still remains same, isn't it? So mg is acting downward, right? So when we displace this, and if you leave it, we know it will try to move towards the initial equilibrium, which is say O here. Let it be O be the initial equilibrium, and say O prime is a displaced so location at which O prime is a geometric location that corresponds to this deflection theta, right? Now when we leave it from O prime, the bob will try to come back, that's mass will try to come back towards this equilibrium, right? And then it will try to oscillate about this equilibrium. So what happens is it will try to oscillate about this equilibrium with time, right? Isn't it? Am I correct or not? So let us say if this is the displacement, right? So this is the initial so this is again my equilibrium location. Equilibrium, right? So when I displace this pendulum, right, what happens is it will try to come back towards this equilibrium, but will continue oscillating about that equilibrium until this disturbance damps out, right? Am I correct? So such a motion where which helps the system to come back towards this equilibrium with time, right, is known as dynamically stable system, right? So that system with this motion, right, that helps it to come back towards this equilibrium, we call it a dynamically stable system. So this is dynamic. Promotes this kind of motion promotes dynamic stability, right? It's why, because see here the amplitude is this much. So with time it is changing. Here it is decreasing, and here it is in opposite direction, right? So if you see, the maximum amplitude is significantly decreased compared to this particular location, right? The initial amplitude. So with time, if this happens, if this amplitude keep decreasing with time, then we can say this is a dynamically stable system. And we can also notice, yeah. So let's move on to the second case as well. Let us say if there is a motor here, which is otherwise, once I displace this here, if I don't allow this to damp, otherwise if you are conducting this experiment in vacuum, right, where there is no air, there is no resistance here. Why this is coming to rest is because of the air resistance. So when we do this experiment in vacuum, it will try to oscillate. Am I correct? What happens is the same system, when we place it in vacuum, say in other words there is no friction at the pivot and there is no damping because of surrounding air molecules, right? So again this is displacement and this is time. X axis is time and we have displacement on y axis. Let us denote it by y, right? So if I displace it by an angle theta, or say displacement here, let us say theta, right? So by an angle theta, so when there is no dissipation of energy in the system, it will try to oscillate, right? So the magnitude of oscillation or the amplitude of oscillation will remain constant since there is no dissipation with time, right? So there is no dynamic. So dynamically it is unstable. Right? Why? Because it is not coming back towards its equilibrium with time, isn't it? So it is trying to maintain the same energy or same amplitude all the time. Right? There is no dissipation here. So what we call this as damped oscillations. So for dynamic stability, we look at damped oscillations. For dynamically unstable system, so is associated with undamped oscillations, right? Is that all? Is that all? Can we expect something else? Or these are the only two possible cases? So for a pendulum, it will be quite non-intuitive to imagine a diverging motion, right? Let us say if I program this at the pivot with with a motor, right, where the motor's RPM or the angular displacement keep increasing, or say if I am adding energy to the system after each and every oscillation, what happens is the amplitude of oscillation increases, isn't it? So say I have initially displaced this by an angle. From there, if the energy once displaced from it, if there is an addition in the energy, so the magnitude keep increasing, it is like diverging, right? So this is like divergence. So this is convergence, isn't it? Subsidence, similar to that of subsidence there. So the magnitude is decreasing in this case. It is increasing in this case. Am I correct or not? So this is like, can you see this? Like this is like e power t, this is e power minus t, similar to that, isn't it? And superimposed by harmonic motion. So the solution can be e power t times or e power minus t times cos of omega t or sin of omega t multiplied by. Isn't it? If you look at this particular signal, the solution can be, yeah, you can guess the solution, isn't it? So here we call this diverging oscillations, right? So case C is where we talked about diverging oscillations. So the last two cases corresponds to dynamically unstable system, right? Whereas the first case corresponds to dynamically stable system. So, but if you carefully observe, in all these cases, the system possesses static stability, isn't it? If you observe this, so after the displacement, say this is the equilibrium, it tries to come back towards equilibrium, isn't it? So even here it is trying to come back towards equilibrium, here it is trying to come back towards equilibrium, the same thing here, right? So the system is trying to attain that equilibrium once it is displaced from the equilibrium, right? So it has that initial tendency. So even in this case it's true, right? So this is our equilibrium. So the system is trying to move towards equilibrium, isn't it? And even here it is the same. So even here. So though it is an undamped oscillation, but still we can see the system is trying to system possess that initial tendency to come back towards equilibrium. Am I correct or not? So consider this case as well. You have that initial tendency to come back towards equilibrium. Right? So though the system is statically stable in all the three cases, we can't claim it is stable system. Why? Because it is not dynamically stable. So static stability may not guarantee the stability of the system, or may not guarantee the dynamic stability of the system. But when a system is dynamically stable, it guarantees the static stability. Right? That is what we noticed here, isn't it? The system here is dynamically stable. That means it guarantees static stability. In other two cases, the system is not dynamically stable, but still the system possesses static stability. So static stability may not guarantee dynamic stability, but dynamic stability guarantees static stability. Okay. So now let's talk about aircraft, right? So first, when we are talking about aircraft, we'll try to divide this stability concepts of aircraft to longitudinal stability and lateral directional stability. And to start with, we'll talk about longitudinal static stability. In fact, we did this during our previous course. So, but still these concepts are important, and it is worth refreshing them, right? So though we are trying to take some time, but still it is good if we visit through this. So what we trying to start with is longitudinal static stability. So just before proceeding to this aircraft, let's now look at this setup carefully, right? So what is that making the system to come back towards this equilibrium? Or what is helping this system to have stability? Can we say something about that? Who is helping here? Who is helping this pendulum to come back towards this initial equilibrium? So let at equilibrium O, the mg is acting perpendicular to the local horizontal, right? And the tension in the string is perfectly balanced by mg here, right? So there is no upward force and there is no rotation, there is no moment, isn't it? Now as soon as you displace it to a new location, mg again acts perpendicular to the local horizontal, right? And a component of this weight, which is mg cos theta. So let us say if you draw a tangent to this curve at this particular location, so tangent to this, and this is theta, this is theta. Why? Because this is theta, right? So because this local horizontal and this string, right, at O, location O, are perpendicular, isn't it? And this tangent is perpendicular to this particular length at this point, so it makes the same angle. And yeah, the same case here. This mg cos theta is perpendicular to this, or say we have this mg perpendicular to this local horizontal. So a component of weight mg cos theta, which is balanced by the tension in the string, right? And a component of this weight, which is mg sin theta, is what helping this object to move in the first place, right? But this motion is about point O, right, isn't it? So with respect to point O, this is now turns out to be a rotational motion, isn't it? So there is a rotation, or so this force multiplied by this momentum is what is rotating this particular pendulum back to its equilibrium, right? So there is a moment that is helping this pendulum to come back towards this equilibrium. We call this moment as restoring moment. So for a system to be stable, we need to talk about its restoring moment. So restoring moment is what is helping the system to come back towards its equilibrium position, right? We call it as restoring moment, right? So we need to understand who is providing this restoring moment, right? Now get back to this aircraft, right? So when you are talking about longitudinal case, what is the possible moment in this longitudinal case? Is the pitch of motion, isn't it? Is the rotation about, or the moment about y-axis, right? Body y-axis, which is the pitching motion. So we need to talk about pitching motion here. Which is given by our pitching motion, what is due to pitching moment which is rotation about or moment about y-axis, right? About body y-axis that we just discussed, right? So pitching moment m is given by half rho v square s cm. So pitch up is considered positive, pitch down is considered negative here, right? That is what we just discussed. Times c bar, fine, where cm is the coefficient of pitching moment. Now when m is positive, if m is positive when pitching moment is positive, right? When the aircraft perform a pitch up motion, right? So that implies cm is also positive, and vice versa. If m is negative, cm is negative. Now let us consider what are the possible equilibrium flight envelopes. So it's cruise. I can immediately name cruise, right? It's a steady level flight. So you can refer to our earlier lectures where we discussed about this. Steady level flight. And then steady climb. Right? And then steady glide. Yeah. Steady glide. So these flight envelopes correspond to equilibrium flight, right? Now consider one such case where you have our aircraft, let's say a steady level flight. This is our FRL, fuselage reference line. Again, this is a reference axis with which all the components are mounted, and it's an imaginary axis again, right? And we have V infinity, means the flow is moving at a speed V infinity towards the aircraft, which means the aircraft is moving at a speed V infinity into static air, right? And this flow is making an angle. So this aircraft is maintaining an orientation alpha with respect to this V infinity called angle of attack alpha, right? And now say if there is a small disturbance, right? If there is a small gust that increase this angle of attack to a new alpha prime, so there is an incremental alpha here. So that means what? You have your initial equilibrium condition is now changed, right? Isn't it? So this change in angle of attack will change the aerodynamic forces, right? Which in turn change the moment as well. So when we are talking about the longitudinal case here, we need to talk about the pitching moment, right? So the change in the pitching moment should result in such a way that we should again go back to this alpha, right? It's not the location or orientation, it's about, we are talking about that state, no, equilibrium state when the aircraft is maintaining certain alpha. So our aircraft has to return to that particular alpha once it encounters a disturbance, right? So that is when we can say the aircraft is stable, at least longitudinally, statically stable, right? Now how this aircraft can return to this alpha? If this aircraft can rotate in such a way that the increased angle of attack is nullified, right? Say now we have the change in angle of attack is nullified, right? So the aircraft now sees a new angle of attack, alpha prime. If I rotate this aircraft in such a way, say if I rotate this pitch down, right, nose down moment, then I can reduce this particular alpha prime to alpha by nullifying this delta alpha, right? So that means there should be a restoring moment by means of this pitching moment, right? Isn't it? So for an increase in alpha, there should be a decrease in, or there should be a negative moment, right? So similarly, when there is a decrease in angle of attack, let us say, so due to some disturbance, there is a decrease in angle of attack. Now this particular angle of attack, so there is a decrease in angle of attack. So this is alpha double prime, right? So now my aircraft has to rotate in such a way that the decrease in angle of attack now should, or say the change in angle of attack should return to the initial angle of attack, right? So from alpha prime, if I have to maintain alpha where alpha prime is less than alpha, what I need to do? I need to rotate the aircraft up, right? I need to give a nose up motion. So that means for a negative change in alpha or decrease in alpha, I need to increase the moment. For an increase in alpha, I need to decrease the moment, right? That is when we can say aircraft possess longitudinal static stability. Now let us consider so let us say Cm is the coefficient of pitching moment variation with angle of attack, right? So this is positive and this is negative. What is positive? We say this is nose up motion and this is nose down motion. Right? Let us consider the following two curves. Let us say if the aircraft is having this sort of variation of pitching moment coefficient, in fact the pitching moment with angle of attack, right? Let us say this is my aircraft A or UAV A, right? Now let's say there is another aircraft whose variation of pitching moment with angle of attack is given by this curve B, right? So this is for UAV 2 and this is for UAV 1. Now, so what is this junction? Can you guess what is this? So what is this location? Cm is? So this is positive, negative, then this must be 0, right? So when Cm is 0, M is 0, moments are 0 here. So can we say this as a trim condition or an equilibrium condition? So what we have is an equilibrium here, let us say alpha EQ, right? Now as we mentioned earlier, so the disturbance that can happen for a trim flight in the longitudinal case is in terms of angle of attack, right? So there in terms of for a pendulum, it is in terms of angular deflection there, right? Isn't it? Angular displacement. So here it in terms of angle of attack. For a longitudinal case, the disturbance that can happen is in angle of attack here, right? So now, when there is such a disturbance here in angle of attack, which has increased it, right? Increased that particular, let us say, but increase the initial trim angle of attack, right. So there is a disturbance now. Because of this disturbance, the aircraft now seeing alpha prime instead of alpha EQ, equilibrium angle of attack, right. So for an aircraft with this particular variation Cm, this particular curve B variation, what happens with the increase in angle of attack, there is an increase in or positive pitching moment, right, which means it will try to rotate the aircraft upwards, right, isn't it? Am I correct or not? So because Cm is positive, it rotates the aircraft up. So what happens in that case? So let us say this is my aircraft, this is my nose, right. So this is my initial condition. So this particular paper cutter points out the initial condition. So when there is, so otherwise you can say this is my free stream velocity, paper cutter is free stream velocity, and my aircraft is oriented in this particular fashion and moving at a level flight condition, right, in a level flight condition. Now when there is increase in angle of attack because of the disturbance, so for the curve, if this particular aircraft possesses the Cm variation as that of curve B, what happens is this will produce a positive pitching moment. So what is positive pitching moment? Rotation, like nose up, right, isn't it? That positive means nose up. So it will increase the, it will try to rotate up, which further increases the angle of attack here. So this further increase in angle of attack creates further more pitching moment, and you will try to move away from this particular equilibrium point. That's similar to the one that we discussed, right? So convex up condition, right? So that means this increase in angle of attack, for aircraft with curve B will create a positive pitching moment. So that positive pitching moment further increases the angle of attack. Right? Further increases the angle of attack. Let's say this is alpha double prime, and this increase in angle of attack will further increase the pitch up moment, right? So you are trying to move away from this particular, so the aircraft with this yellow graph, right, yellow variation will try to move away from this equilibrium position, right? So you are trying to move away from this equilibrium position, right? That means the aircraft is said to be unstable, statically unstable here. If the aircraft possesses this particular variation, we say the aircraft is statically unstable, doesn't possess longitudinal static stability, right? And on the other hand, if the variation, otherwise if the disturbance reduces the angle of attack, say subscript 1, right, alpha subscript 1. So if the variation reduces the angle of attack, for example, if this is my free stream velocity, right, this paper cutter represents free stream velocity, and my orientation with respect to this represents angle of attack of the duster with respect to this free stream velocity is angle of attack. Now this has reduced the angle of attack. So the disturbance now reduced the angle of attack here. What happens is, so this yellow curve will produce, due to that it will produce a negative pitching moment, right, isn't it? This is the negative axis here, right? So this is, so it will try to pitch down the aircraft. So say this is the initial angle of attack. Now there is a decrease in angle of attack. So because of the external disturbance, and now the aircraft will try to further rotate it down, which means it will further decrease the angle of attack. So you will try to move away from this equilibrium location. So you will try to reach another angle of attack or reduced angle of attack, right? So angle of attack is decreasing in this direction, increasing in the opposite direction, right? This is the increasing axis of alpha, right? So this pitch down moment will further reduces the angle of attack, which will also produce a higher pitch down moment, isn't it? Higher nose down moment that will take you away from this particular equilibrium location. So this alpha is moving away from this alpha EQ. So for the aircraft with this yellow curve, you are trying to move away from this equilibrium location, right? So on the other hand, when you talk about this aircraft with this this red graph, right? If the variation of pitching moment follows the curve A, the UAV or the aircraft which follows this curve A, so when there is a change in angle of attack, which is an increase in angle of attack because of the external disturbance, so this will produce a negative moment, right? So when there is an increase in angle of attack, so the aircraft with curve A will try to produce a negative moment, right? Negative pitching moment, which is pitch down moment. So we have initially this particular orientation, and due to external disturbance there is an increase in angle of attack. So this produces a pitch down moment that decreases that, right? So the increase in angle of attack with this from this curve will produce a negative moment. So that means the aircraft will try to pitch down, right? So this pitch down will decrease this angle of attack, right? So it will decrease the angle of attack, which helps you to move towards the equilibrium. On the other hand, when the external disturbance decreases the angle of attack, so the aircraft with curve A will produce a positive pitching moment that will help the aircraft to rotate nose up, right? So which increases the change in angle of attack, isn't it? So it will try to increase the angle of attack. What is the increasing direction of angle of attack? Towards my right. So from here you are trying to move towards this point alpha EQ. So you are trying to move towards equilibrium location, right? So one condition that we can observe is the slope here. If you look at the slope, the change in pitching moment due to change in alpha, right? So this corresponds to alpha 1, alpha 2, the change in alpha. So the change in pitching moment or this change in angle of attack should be negative, right? Or less than 0 here. You can see. So at this alpha 1, right, alpha double prime, you have a higher pitching moment here, right? And alpha prime, which is higher than alpha double prime, you have lower pitching moment. So the change is negative. There is a negative slope here. You can see there is a negative slope. So the Cm versus alpha, the Cm variation with respect to angle of attack should be negative. So this is one important condition that we need to maintain for a static longitudinal static stable flight, right? And is that all? Is that sufficient enough? So let's consider another plot which is just parallel to this red line, right? Say the slope is negative. The slope is negative here. Okay. So we have satisfied this condition. dCm upon d alpha is negative, right? But which curve do you prefer for the aircraft to possess? Yeah, A. Okay. Why we need A? So if you look at this, right? So the alpha trim here. What is the trim condition for this particular aircraft? When is Cm is 0 at this particular location, isn't it? So where at this particular location you have negative angle of attack. Alpha is negative, right? So you will not be able to trim the aircraft at negative angle of attack, isn't it? You will not be able to fly the aircraft at negative angle of attack. So you should not trim it at negative angle of attack. So the necessary condition is that you should maintain this particular coefficient, which is Cm at alpha 0 should be positive. So this Cm at alpha 0 is the y-intercept here, we call it as Cm naught. Cm naught has to be positive, has to be greater than 0, and Cm alpha has to be less than 0, right? So these are the two conditions. So this is the necessary condition. And we have this as sufficient condition. Okay. So our aim is to look at what is the contribution of these various components of the aircraft. Say we looked at various major components, right, like wing, propulsion system, and tail, and vertical tail. So how they are contributing towards this Cm alpha and Cm naught of the aircraft, right? And we should never forget that these moments we are talking is about CG, center of gravity of the system, right? It's about the CG of our aircraft, right? So with respect to that, how these components are contributing towards this stability, right? So what happens when I add a tail? What happens when I add a canard? What happens when I have double biplane wings, right? So if I have to design a UAV, say if I have to design a biplane UAV, I need to understand whether the addition of these two wings, is it contributing towards stability or destabilizing the system, right? That's the main aim here. So we'll try to look into those in the coming lectures. So this is the necessary condition. I think in our previous discussion this was fact, right? So try to correct this. So this is the necessary condition to have Cm naught positive and Cm alpha negative. Sufficient condition is Cm alpha should be negative. So for those aircraft with Cm alpha greater than 0 and Cm naught greater than 0, so that we can still fly those aircrafts, right? But with an onboard controller. Okay. But even if Cm alpha is less than 0, if you have Cm naught less than 0, you may not be able to fly the aircraft. You have to trim at negative angles of attack. At negative angles of attack, you will try to reach towards CL0. You don't have lift, right? So, yeah, see you soon.